CI, but I know there's a misprint. Okay, so first of all, I would like to thank the organizers for inviting me to give a talk at this interesting conference. So the work that I will report on was done in collaboration with Pierre-Yves Castet, with Roma Aljanik, and with my student Andrea Rose. And the details of what I'm going to tell you can be found in this preprint, and it will also soon appear in JHEP. Okay, so this is the outline of my talk. So maybe it's not clear from the title, but the theme of my talk is non-planar corrections to n equals 4 super Young mills. So I will start by some introduction, where I tell you what is known about 1 over n corrections, in particular 1 over n corrections to short operators and to BMN operators. Then I will describe to you a proposal we have for how to calculate matrix elements of the non-planar dilatation operator for between operators which are dual to spinning strings. And after that, I will introduce and solve some toy model which describes string splitting and joining, and I will use that toy model to get an estimate of the scaling behavior of the genus 1 energy correction to spinning strings. And then, not surprisingly, I will finish with some conclusion. Okay. So first of all, let me remind you that the non-planar dilatation operator is actually a known quantity. More precisely, it is known in the SU2 sector to 2 loops, where by the SU2 sector I mean multi-trace operators built from 2 types of complex scalars, Z and phi. Now in this talk I will only deal with the 1-loop dilatation operator, and in its full form it can conveniently be written like this, where these checks here denote the functional derivatives. And the full dilatation operator at 1 loop can be split into a planar part and a non-planar part. And the planar part takes this form here, and as we all know, can be identified as the Hamiltonian of the Heisenberg spin chain, as shown by Minahan and Zarembo. This operator P is a permutation operator, which permutes the spins at site k and k plus 1. Now the non-planar part can be written in various different ways, but one way is this one here. So it also involves some term 1 minus a permutation operator, but now the sum is over all non-nearest neighbors. And then there's some sigma operator appearing here, which one can denote as a splitting joining operator. And you should also notice, of course, that the non-planar correction is down by a factor of 1 over n compared to the planar term. Okay. Okay, so here I have illustrated the action of the sigma operator here on a single trace state and here on a double trace state. So the sigma operator can either split a trace, 1 trace into 2 traces, or it can join 2 traces into 1, as indicated by its name. Okay, so what is known about 1 over n corrections? Let me first discuss short operators. So what do we know about these? Well, first of all, the 1 over n corrections are easy to evaluate, and that is because the non-planar dilatation operator acting on O involves only a finite and small number of operations. And since the operator is short, then the diagonalization problem involves only the diagonalization of a matrix of a finite small dimension. And even though the problem is then easy, there are important lessons to be learned. So here I have listed some of them that we have already learned. So one thing we have learned is that the anomalous dimension does not always have a well-defined expansion in lambda and 1 over n, although the dilatation operator has. And the reason is simply that the deltas are eigenvalues, and they do not need to have a well-defined expansion in lambda and 1 over n, even though the matrix elements have such an expansion. Another thing one learns, and that's quite generic, that if you have degeneracies in the planar spectrum, you get energy corrections of type 1 over n, as opposed to type 1 over n squared, which you get when you don't have degeneracies. And then finally, an observation that I think you all know, that we see from this analysis of short operators that integrability is likely to break down beyond the planar limit. And let me remind you that this is because there are certain degeneracies in the planar spectrum which can be explained by the presence of an extra conserved charge, and these degeneracies disappear when we go beyond the planar limit. Okay. So let me go to a slightly less simple example, namely the example of BMN operators. So BMN operators are operators of this type here, where we have a large, namely J, number of Z fields and a small number of impurities in the form of phi fields. And we're interested in the BMN limit, where J goes to infinity, N goes to infinity, and lambda prime, which is lambda over J squared, and J squared over N is fixed. Now this case is almost tractable. First of all, we know the planar problem can be solved, and the spectrum of anomalous dimensions has been successfully compared to the spectrum of strings quantized on the PP wave. Okay. Furthermore, acting with the non-planar dilatation operator on a BMN operator is also relatively simple. It involves only a finite small number of operations, and that is of course because many of the fields inside a BMN operator are identical, so 1 minus the permutation operator vanishes. However, when we want to diagonalize the non-planar dilatation operator, we run into complications. And these complications appear for all states except for the lowest one. Namely, it turns out that we face a huge degeneracy problem. Although we can formulate the diagonalization problem as a simple quantum mechanical problem, the actual diagonalization involves some non-trivial problem of generate perturbation theory. We have to diagonalize a complicated infinite dimensional matrix. And this problem, I remind you, was actually never resolved. And then there was also a complication that the comparison to string theory, more precisely to string field theory, remained inconclusive. Okay, so now I propose to go on to something even more complicated, so to say, namely operators dual to spinning strings. So these operators are of this type here, where we have J1 Z fields and J2 phi fields, and we're interested in the limit where both J1 and J2 go to infinity, but J1 over J2 is finite and fixed, and lambda over J squared as well, and J squared over N. And we also know that in this case the planar problem is solvable. But now the non-planar problem seems almost intractable. So why? Well, first of all, acting with the non-planar dilatation operator on such an operator here involves an infinite number of operations, because there's an infinite number of both phi fields and Z fields, and they're mixed in all possible ways. And of course, we can also expect an even larger degeneracy problem for these operators. And finally, we have no string field theory results to compare with, only some semi-classical considerations that I will return to later. So now what we propose is, in order to circumvent these three problems, for the first one, to use the coherent state formalism describing spinning strings that Niklas also described earlier this morning. And then to circumvent this one, or to bypass it, to use some toy model, which is not the actual model, but which can be used to get an estimate of the scaling of the genus 1 contribution. And then, since we have nothing to compare with, we suggest that maybe one could use our results to formulate an effective string field theory for the decay of all of cycling strings. But I must admit we did not get very far on this point here. Okay. So let me remind you of the spinning strings. So more precisely, I'm interested in a folded spinning full of cycling string, which has two large angular momenta on S5. And we know from classical string theory that its energy has an expansion, at least to the first few orders, which looks like this. Starts out as J, and then some lambda over J squared times some energy epsilon 0. And this part here I can reproduce using the planar dilatation operator. Okay. So what happens if we take into account string interactions. Well, actually, we don't know much, but there were some considerations by Peter, Plewka, and Samaklar, which suggest that one can do the same analysis as in flat space, and that implies that such a folded spinning string can spontaneously split into two folded strings at any point x along the string at any time. And then the two string pieces evolve according to the classical equations of motion with initial conditions given by the values of the field at the moment of splitting. Okay. What should we then expect for the energy correction resulting from string splitting and joining? Well, if we expect naive BMN scaling, consider the limit where j and n go to infinity, and lambda or j squared and j squared or n are finite and fixed, then we will expect that this energy contribution here should have a genus expansion which looks like this. And well, the guy that I will try to say something about is this one here. Okay, so let me stress that these semi-classical considerations that I just mentioned, they just serve as a source of inspiration for our work, but our work has nothing to do with string theory. We work entirely in the gauge theory language. Okay, so let us assume that we have an operator dual to the folded spinning string, and that operator is then an eigenstate of the planar dilatation operator with eigenvalue epsilon 0. So it's just a folded simple string like this, and forget for the moment about the thesis here. Now we can also consider a string where we cut this one into two and glue together the two ends. Then we get two closed strings, and we have an eigenstate of the planar dilatation operator with the same eigenvalue at least up to 1 over j corrections, because we change only the values of the field at one point for a very long operator. And the same if we cut the string into L pieces where L is much less than j. And now we wish to calculate the matrix elements of the non-planar dilatation operator between an uncut state and a once cut state, or vice versa, and all the generalizations where on the right hand side we have a string consisting of n plus 1 pieces and n pieces and n pieces here and 1 plus 1 pieces here. Okay, so let me make it completely clear. What we want to calculate is this type of matrix element. And okay, these types of matrix elements and their generalizations. Okay, so here you should notice that, of course, again, we have a problem of degenerate perturbation theory, because all these multi-cut states are degenerate in energy with the uncut state. And you should also notice that, well, we consider only the straight cut states. In principle, we could also cut with some more skewness, but we expect the skewness not to matter in the continuum limit. And of course, if we cut with a too large skewness, then we move out of the state of the space of degenerate states. So we stay with straight cut states. Okay. And how do we deal with these folded strings? Well, we use this coherent state formalism that Niklas explained this morning. So we introduce an SU2 spin 1/2 coherent state in this way here, where Z and phi correspond to spin up and spin down, and they have these canonical inner products. And the parameters theta and phi, which live in these intervals, parameterize a unit 3 vector in this standard way here, as Niklas also explained. And now, using this formalism, a spin chain state for a chain of length L can be described as a direct product of coherent state vectors, one at each side. And then you have, of course, an angle theta k and phi k for each side in the chain. And you consider this situation where these theta k's and phi k's vary slowly, and you send j to infinity. Then you recover exactly the Frolov cycling limit, and in that limit, as Niklas also explained, the spin chain is described by an effective sigma model action, which looks something like this. Okay, And if you write down the equations of motion for that sigma model, you find among its solutions the spinning folded full cycling string. And for that solution, the angular variables theta and phi look like this. So phi is constant along the string, but theta varies between minus theta 0 and plus theta 0. So the string looks something like this. And I take the coordinate of the string to run between minus 1/2 here, minus 1/4, 0, 1/4, and 1/2. And these two conditions must be fulfilled in order for the string to be closed and to be folded exactly once. And in this formalism, you find the planar energy of the string by taking the expectation value of the planar dilatation operator between the states composed of coherent state vectors. And if you do the calculation, you find some expression in terms of theta prime, and if you do the integral, you find some expression in terms of elliptic integrals. And in this picture here, the cyclicity of the state, which we know must hold, is expressed somewhat implicitly. Namely, it's expressed by saying that the momentum along the string p sigma must equal to 0. Now this fact that this cyclicity is only expressed via this p sigma is actually a problem for what we want to do. And the problem is that as this formalism here, it singles out the endpoint of the string. It gives a number to the first. It says that something is the first point of the spin chain and something is the last. And you can see it particularly in the inner product between such two direct products of coherent state vectors. If you take two such direct products of coherent state vectors, the inner product is first a delta function in the length, and then you have to take the inner product between each coherent state vector at each side. And note in our case, because one of the angles is constant along the string, this inner product is just some cosine, theta I minus theta j. But now the problem with this is that the endpoint of the string becomes a bit ambiguous after cutting. First of all, you could take either one, the original endpoint as an endpoint or the cutting point, but that's actually not all. You're also allowed to do some translations along the string, which you will see if you sit down and do the calculation. So in order to deal with this problem, we introduce some explicitly cyclically symmetrical states. So instead of having only this direct product along the sides of the chain, we take a sum of such products, where in each product we have translated the index of the vector by 1. And with these states, we have to calculate the planar energy in basically the same way as before, but we must now divide by the new normalization. Okay, so to calculate the two matrix elements over there, I need the normalization of the uncut string and the string which is cut exactly once. So let me just give you an example of how these calculations work. So for this uncut string, I have first the product or the inner product between the coherent state vectors at each side. Then I must sum over all translations of the two sides. But one sum I can pull outside as a factor of j. And then the second sum I can rewrite as an integral, and that gives another factor of j. The inner product itself is something, the product of cosines, and I can exponentialize it in this way. And the sum in the exponent also turns into an integral. And if you do the calculation and expand this guy here for small delta, then you find what appears here is theta prime squared, and that was exactly the integral which appeared in the planar energy. And in this way you find in the end this normalization factor here for the uncut state, where j is the length of the string and epsilon 0 is the planar energy. And if you do the same for the once cut string, you find something very similar. You get one length factor for each piece. So one is L1 times j, the other is L2 times j, where L1 and L2 are given by these expressions. And then you also have a square root for each piece, which involves the energy of one piece and the energy of the other piece. Okay, so now we want to calculate the matrix element for string joining. So we want to act with the non-planar dilatation operator on a string which is cut into two pieces. So I remind you that the non-planar dilatation operator looks like this, where this guy here is the joining operator. So the way in which the non-planar dilatation operator can join two pieces can be illustrated in this way here. So this double sum here, it picks out one point on one piece of string and another point on the other piece of string, and then it joins it together. So here are the four possible locations of the 2 points which are joined together. Okay, and now it turns out that these diagrams in the lower row are subdominant, and the two up here give the same result. And one thing you can also notice is that this sum over translations of coherent state vectors can actually be factored out from this state here on the right-hand side, because the non-planar dilatation operator actually already has a sum over points on one piece of string and points on the other piece of string, and take another two sums just multiplies by some factor of L. Okay, and then when you do the calculation, well, yeah, okay, symbolically, you take the two pieces which are glued together and split them into 4 parts, 1, 2, 3, and 4, where 1 is from this corner up to here, 2 is the next, and 3 comes here, and 4 is the last one here. And then you similarly, you split the uncut string in 4 pieces, and you take the inner products between the two, and then there's some anti-symmetrization factor here coming from 1 minus the permutation operator. And well, yes, then you just simply have to sit down and do the computation with a strong cup of coffee, and then you get from the inner products you get some exponential which looks like this, which looks like some simple Gaussians, but there's some curious alpha cube here. And from this exponent, you see that since J is large, the only case where this factor here becomes important is when alpha is equal to beta and delta is small, and in that limit it can be expressed simply like this with a theta prime again. And then you have to plug all that. Well, now you have to do the sum over alpha, beta, and delta, and that gives, of course, 3 integrals, which gives you 3 factors of J. And then you have some additional factors of J from this translation of the states that you introduced, and you have to remember some normalization factor. And if you do the computation, then you find a final result which looks like this. Where again, these L1 and 2 and L0 are the lengths of the 3 strings which enter. In particular, L0 is 1 here actually, and L1 and L2 are given in this way here, where X is the cutting point. And you also find some factor involving the energies. Yes, and what can we learn from this? Well, you see that you have some rather curious scaling behavior here. And then you see that this matrix element, it depends on the point of cutting via some Jacobian Cn function. But then it also depends on it more implicitly in these length factors here and these energy factors here. You can also notice that this result can easily be generalized to the case where we have L pieces of string on one side, or L plus 1 piece of string on one side, and L pieces of string on the other side. Then we get a similar result. Only these 2 factors here involve only the lengths and energies of the pieces which are actually involved in the interaction. Okay, now I want to calculate the matrix element for chain splitting. And again, I remind you that this non-planar dilatation operator involves this double sum over points on the spin chain. And I start from some uncut chain, and now I can cut it with the non-planar dilatation operator. So first I pick 1 point on the string where I cut, but since I have to get a non-zero overlap with what I had on the left-hand side, the position of the other point is completely fixed. And that actually means that there's one sum in this non-planar dilatation operator which is killed. And that means that we get 1 J factor less for this type of matrix element than for the other one. But we should not be worried, because Even though it means that the non-planar dilatation operator is not Hermitian, it is still related to its Hermitian conjugate via similarity transformation. And that is a situation that we saw before also for BMN states. Okay, so in this case we can parameterize the place where the cutting took place by some parameter gamma, which is the distance from the cutting point of the operator we have on the left-hand side of the matrix element, and then this operator here. And we must, of course, sum over this gamma. And down here, we see that this, just as before, because the non-planar dilatation operator already has a sum over all points on this string, then this extra sum from the translation of the coherent state vectors, it factors out as a factor of j. And what is left is a sum over this gamma and over the two translations of the two string pieces on the left-hand side of the matrix element, and then this anti-symmetrization factor. And again, now you simply have to sit down and calculate, and you split the calculation into 4 different pieces. So for this one piece is this one, and then the next one is this. The third one would be this one, and the last one, this one up here. But that is just a matter of the organization of the calculation. And when you do everything, you find a result which looks like this. It's almost as before. The only thing which differs is scaling with j. There's 1 power of j less, and then this term here is upside down. So again, we have a very curious j scaling, and again, it's easy to generalize this matrix element to the case where you have some spectator pieces of the string. And again, the dependence of what changes if you introduce some spectator pieces of the string is only the factors here which refer to the string pieces which are actually involved in the interaction. Okay. Well, so what can we learn from this? Well, we would like to say something about the genus 1 energy correction to fall of cycling strings, but this is, of course, very difficult because we have an infinite matrix that we want to diagonalize. So we try to instead introduce some solvable toy model for string splitting and joining. So this model builds on the assumption that first the non-planar dilatation operator or matrix or operator is Hermitian, and secondly that the matrix elements depend only on the point of splitting or joining. So let me stress that this is not the case for the matrix elements I had, because we had a dependence on this point of cutting, but we also had a dependence on the length of the pieces which were cut. Now this gives us a very simple model. So if you assume that you have a spin chain where you can just cut at 3 sides, then you get the possible states which look like this. Here's an uncut state, a state cut at point side 1, a state cut at side 2, a state cut at side 1 and 2, and so on. And then you can write down under these assumptions what the matrix that you need to diagonalize looks like. And it has some simple structure. So you see that when you go from one step to the next, you place on the diagonal what you had before, and then on the off diagonal you put some diagonal matrix with the newly introduced matrix elements. And this is a matrix which can actually be diagonalized exactly. So in the case where we only have 3 sides, the possible eigenvalues are simply all the possible sums and differences between the 3 different matrix elements. And if you have a very large matrix of the same type, then you find that your eigenvalues lie in a continuum between minus j times this integral and plus j times the same integral. Okay, so let's try to apply this to our case. So we don't want to insert the exact values for this chi x, but let us just insert what the scaling with j is. So if we do our similarity transformation to get something Hermitian, or get the same scaling of all matrix elements, rather, then we find that this chi x scales as j to the power minus 5 over 2. And if we insert this into the energy correction, then we get lambda over n, which was the prefactor of the non-planar dilatation operator, and then we get from here a j half from the integral, and then we put outside a chi 0, which we just replace by j to the minus 5 over 2. So we get a scaling which has a j to the power 7 over 12. Okay, and that should be compared to the naive BMN scaling, which simply looks like this, with simply 1 power of j. So apparently we get some unexpectedly small power of j. Okay, so what can we say about this result? Well, first of all, let's assume we accept it. So what can the possible interpretations be? Well, first of all, it could be that the naive BMN scaling does not hold, but then on the other hand, we don't know if it should or not. We know that BMN scaling breaks down already at the planar level, but at a higher loop order, and we actually don't know anything about the BMN scale at this place. But it could also be that the contribution to the genus 1 energy shift coming from these semi-classical processes is actually just small. So we had to assume that, that the string splits into finite pieces of string, but maybe it's much more likely that it splits off very small pieces of string at well, okay, but then there are of course various problems with this scaling matrix element. First of all, as I already said, our matrix elements do not only depend on the point of splitting and joining. It also depends on the previous points of splitting and joining, so to say, the length of the string pieces involved in the interaction process. And then there is, of course, the problem whether we are really allowed to consider only these straight cut states. Should we really integrate over some small skewness parameter at some intermediate point in the calculation, and would this give some additional factors of j? Okay, finally, let me conclude. So what can we say? Well, we can say that we have suggested a method to study non-planar corrections to Rudolph cycling strings. We have observed a curious scaling behavior, and we have found some indication that the genus 1 energy shift coming from semi-classical processes is small. And what should we do then in the future? Well, we should maybe try to understand this curious j scaling, and eventually we would like to formulate some effective string field theory based on our two matrix elements here, which describes the decay of the Rudolph cycling string. But we have not really been able to make any progress on this. Okay, I will stop here. Thank you.
Of a two-string eigenstate of the planar rotation operator?
Up to order 1 over j corrections.
So it's not an exact?
It's not an exact eigenstate, no. Eigenstate.
And then shouldn't the quantity, so you just computed matrix elements so far. But the interesting thing would be to compute decay rates. So you would have to make sure that your state x is degenerate in energy with state 0.
Yes, but
is that possible? Because it's
no, but
because
well, okay, but this
the
is an
problem I have is because when you use this coherent state, you sort of cut it somewhere and glue it together.
Yes, yes.
And I mean, we had also been thinking about it, and it seemed to me the problem was that you would always have a discontinuity because if you have your configuration, and you would just
yes, but you also have that in the string picture, right? You cut the string somewhere. But I'm not claiming to be exact. I just say that this is an eigenstate up to terms of order 1 over j. And since this is a very long state, then...
but how would you then really project on a degenerate two-string state? Is that clear in your formalism? I mean, how you would compute a decay rate?
Well, I'm working entirely in this gauge theory language, so I'm not really saying anything about decay rates. I'm calculating matrix elements of the non-planar dilatation operator. That's all what I'm doing. So maybe we can discuss.
These coherent states you're using, they are overcomplete, yes? They are not orthogonal. Did you have to correct for that?
It's somehow hidden in the formalism. You have to divide out the normalization of states. I think that is it.
Okay, thank you very much.